Right, good morning, everybody. Today is the 11th of February 2021. Going through our fifth practice paper. I think I've got about three more that I can give you. We try to do I try to do around about 8 practices prior to the foundation program exam, so that you're very sort of used to the style of questioning, and it just gives you the best chance possible of scoring getting a good grade. First of all, just some overall feedback. Obviously, I've fed back to those of you who've handed the work in. I've marked it and fed it back, so you see how well you did. I think the formula that we have, whereby we're doing the walk, whereby you're practicing exams, and then I'm doing a walkthrough afterwards, that seems to be working very well. So we're going to keep with that for now. But obviously, do have in the back of your mind any topic areas you want me to go over. Obviously, that'll be important after the half-term break. So I'm just going to warn you, just to let you know, that I am recording this. I am recording this video, and it will go up on YouTube, so that you can watch it again if you need to, but also so that anybody's missed the lesson because they're halfway around the world or whatever, so that they can sort of watch it and get the best they possibly can out of it. Obviously, if you have questions or you spot anything that you don't think's right, that is your opportunity to speak to me. So please do either pop something into the chat box, or put something, or just turn your microphone off and just ask. You know that I will happily stop and go over something in more detail if you need me to. By and large, from what I saw that was handed in, the understanding is getting ever better. It really is. Every single time I'm seeing development. There are some distinction scores. One or two people are still not really completing the paper, just doing the first couple of questions and then sort of stopping. Not quite sure why that is, but I do think that really, those of you who haven't completed the paper, you really could do with watching the walkthrough and actually completing the paper with the benefit of the walkthrough, so you understand how to answer the questions. That's assuming that you're not handing in everything because you don't fully you don't fully understand the topics. So if we go through it, obviously we've got our formula sheet on the first page, and then we got our first question. Always the first question is about units and uncertainties. So it's just some basic sort of what I sometimes refer to as housekeeping. Now, suggesting the uncertainties. So you got a fairly standard question. I think you've seen something very similar to this before. Just want to make sure that we can sort of get the best we can out of this question, because it's a very easy few marks if you know what to do. So suggesting the uncertainties of the equipment first. So the stopwatch is used to measure the time. So that's going to be plus or minus 0.1 seconds. And the ruler, well, that's going to be nearest centimetre, so plus or minus 0.01 meters. That's all there is to that. Most people who do attentively got it right. Now the next one, it says you've got to calculate a mean and use an appropriate number of significant figures. So if you actually work this out as a mean, it comes out as 1.6 reoccurring. But what you need to do is go to the nearest two significant figures. If all your values here are two significant figures, you should use two significant figures here. I gave the benefit of the doubt for those of you who rounded it off to 3, because you can sort of get away with that. So really the correct answer was just the average. It was 1.7. I think those who were making the mistakes with the means, whereby forgetting to press equals before the divided by 3, I think we've cleared that one up. So then we're looking at calculating the absolute and percentage uncertainty in the measurement of time taken to roll down the slope. So the time taken here is, well, it's anywhere between 1.3 and 2.0. That's your maximum minimum. So these are the two values you're interested in. So it's the range. Okay, there's your range. Divided by 2 gives you the absolute uncertainty of 0.35. Now, when you're quoting an absolute uncertainty, you should put the plus or minus in front, and you should also put the unit. So then you want to work out the percentage uncertainty. Well, that's your absolute uncertainty divided by your mean value. Now, those of you who used 1.67, yours are slightly different, but it came out to be 0.206, which is to the nearest percent, 21%. You multiply that by 100, you got 20.6. You can quote percentage error to the nearest percent. So there's that was the first bit. Generally answered quite well, which is why I'm going over it quite quickly. Pupil uses the formula below to calculate the acceleration due to gravity. Well, it's actually the acceleration of the ball, it should actually be. So if we want to first of all show that the equation is homogeneous. So homogeneity is just basically looking at the base unit. Use the SI units. Hi, yeah, are you okay?
Yes, I'm good.
Okay. So we're looking at the units over here. So units of acceleration, you should say meters per second squared. Time squared is second squared. And that's 2, which doesn't have any units. And that is h, which is in meters. Then what you do is you show your cancel. You show it cancelling like that. And that's all you needed to do. It's pretty simple. Then you have to calculate the acceleration of the ball, giving the correct units. So the acceleration is going to be 2h over t squared, which you get from the table. The height is 1.98. So the ramp length here was 1.98. Divided by the t squared. The time was 1.7 or 1.67. Again, if you use 1.67, you got slightly different values to me, but I still gave you the marks because it was correct. So 1.7 squared, that makes it 1.37 meters per second squared. You had to quote the correct unit to get the mark here, okay? Now it's a simple calculation. I mean, it's sort of GCSE level stuff really. So you only got 1 mark for that one. So now you've got your big E, which is calculating the percentage uncertainty in the pupil's measured value of the acceleration of the ball. Now, most of you got that right. So you want to get the percentage uncertainty. That's the uncertainty divided by the value. And we know that if we're multiplying or dividing, we've got to add the percentage uncertainties. Now, because you've got t squared, obviously you've got to add an extra percentage uncertainty of t. So it's 2 times it. Now,
so the 2 before the h doesn't have any effect on it?
No, it doesn't, because the 2 itself is just a number, isn't it? So that's an absolute number. It's not got an uncertainty. It's just a number.
All right.
Okay, good question. Thank you. So as we move on, so delta h over h, well, it was the nearest centimetre divided by 1.98 plus 2 times. Now we've already calculated this. I calculated it to be 0.206 because we worked it out before. And that's where going to the extra significant figure in your working makes your life a lot easier, because here I calculated the percentage uncertainty is 0.206, which was approximately 21%. Okay, so relatively simple to do. It's something that we can kind of do almost in our sleep now. So 0.417, that's what it comes out to be, but by my reckoning, which is about 41.7% or 42%. Now that's my final answer. I double underline it so that people can see that it's my final answer. You got 1 mark for sort of showing the correct physics, 1 mark for substitution, 1 mark for expressing it as a percentage uncertainty, because the question asked for a percentage.
Gary, how did you get 0.01?
Because that's the uncertainty in the height. If you the uncertainty in the ramp length, which I sort of changed it, which was h. See, my percentage uncertainty is going to be the uncertainty in the ruler, 0.01, divided by the value. Does that make sense?
Yeah.
Now this one was a bit of a tricky one. Very few people got this one right. The student suggests that using a ruler with a millimeter scale instead of centimeter near a centimeter to obtain a more precise value for the length as a possible improvement. Explain whether you think this will improve the quality of the results. Well, although you might think it would, it actually doesn't. If you, again, you sometimes you have to take a little step back in these questions and think about the context. So this is the two particular things here are that the main part is obviously that it's not, it won't improve it. Why? Because if we take a step back, we realize that that percentage uncertainty there is tiny compared to that. That's about 0.5%. That's about, the time is going to contribute about 40%. So no, timing, and that's because timing was the greatest source of error. Okay, so that's the idea. And basically what you got a mark for the statement and one mark for the explanation. So no, it doesn't, because timing is the greatest source of error. Because although yes, using a millimeter scale would improve the precision of the measurement of the length of the ramp, actually it won't really greatly improve the quality of the results, because it was actually the timing that makes sense. So sometimes in this last part of the question, you're asked to suggest an improvement with a reason. Sometimes you're asked to suggest an improvement, you're given a suggested improvement, and you have to discuss whether or not it actually will help improve the quality of the results. Now, you have to really sometimes stop and think about the actual experiment itself. So, for example, in the previous one where we're talking about sort of something being sort of, being sort of thrown upwards, you had to stop and think about sort of the physics behind whether, the sort of the physics behind how you'd measure the maximum height or how you'd measure the timing. It's a thinking question. Really, this is getting onto sort of the merit and distinction level sort of assessment. So, because remember that the papers are really, if you're scoring 40%, that's a pass. But we want to have the slightly more challenging questions for the merit and distinction level students to really sort of show how good they are. So that was the first question anyway. So the second question is always a dynamics. It's always a bit of an engineering-y type question. So in this case, I chose a context of a Eurofighter Typhoon, which is designed to fly very fast. And you've got a data table which contains information about the aircraft that you'll need to use throughout the question. The typical mass of the aircraft, you're given the mass, you're given the cruising speed, you're given the maximum force from each engine, you're given the number of engines, and you're told how much energy there is in each kilogram of the aviation fuel. So the first one is quite an easy one. You had to calculate to show the maximum acceleration according to the data above of the aircraft is approximately 11 meters per second squared. So here, well, you can use SUVAT. Well, no, because you've got a change in velocity, but you haven't got a time or a distance, so you can't use SUVAT equations. But you are given the mass and the force, so you can work out the acceleration from Newton's second law of motion using F equals ma. So we quote the formula, rearrange, substitute. Now here, got to be careful. If you look at the picture, 1, 2 engines. To be certain, actually tells you there are 2 engines, and each engine produces 9 times 10 to the power of 4 newtons. So it's 2 times 9 times 10 to the power of 4 over the mass, which is 16,000, which is then going to be 11.25 meters per second squared, which is approximately equal to 11 meters per second squared. Okay, so here as a marker, I would be looking for really either the substitution or the answer to some extra significant figures. don't skip the calculation step, okay? 2 reasons. First of all, it's not completing the question. The second reason is if you've got your working wrong, if you do the calculation step and it's nothing like the value that it's supposed to be, then you know that there's a mistake. You can go back, you can correct it. Whereas if you just write that bit out and then don't bother doing the calculation, just say it's approximately equal to 11, if you've got that bit wrong, and I am going to spot it, you don't get the mark. So B part 1, you have to calculate the minimum time taken to accelerate from rest the aircraft's cruising speed. So we're ignoring air resistance and friction or anything else, which is a bit inaccurate, but never mind. So we want to use the idea that the acceleration is the change in speed divided by the time taken, or sometimes that's expressed as V minus U. But here the change in speed, well, it's going from rest, so that's 0, up to the cruising speed, which is 500 meters per second. So it's 500 divided by T equals 11.25. So the time is going to be 500 divided by 11.25, rearranged it. So that then comes out to be 44.4 seconds. Okay, so relatively straightforward. A good GCSE student would probably be able to do that. Next one possibly might be a bit harder. So we've got to calculate the distance traveled during this period of acceleration. You could use lots of different CVAT equations, but really want to try and avoid using time because we calculated it here. And although errors carry forward, we want to try and get it right. So we've got to think about SUVAT. So we write out SUVAT. What are we given? Well, we want to work out the distance traveled. We know the initial speed is V. We know the cruising speed is 500 meters per second. We know the acceleration because we've given it. So even if you couldn't work it out, you could just get it from here. So we know that one. So what we're using is V squared equals U squared plus 2AS. So we rearranged it to make S the subject. S equals, well, it's V squared minus U squared over 2A. Substitute. V squared, well, that's 500 squared minus U is 0. I could put the square there, but it's immaterial really. Plus 2 times, well, I'm going to use my value of 11.25. You can use 11 as long as you show you're working. So substitute, do the calculation, and I made it 1.11 times 10 to the power of 4 meters, okay? Or 11,000 meters or 11 kilometers, which is a reasonable value when you think about it. If you've got a fighter jet, it's going to take several kilometers to, to sort of get up to full speed. So next part is to describe and explain how the acceleration of the plane would be different to this value in real life. Well, in the question, we're assuming that there's no air resistance, that there's no friction, and that the acceleration would be constant. So the acceleration would actually decrease. The acceleration would decrease at higher speeds. Due to, well, you could say due to air resistance, or you could just say drag forces. Okay. Now, there's a little bit of a proviso here. With something like a jet plane or a car or a motorbike, it gradually uses fuel. There's a difference here. If ever you get a question about a rocket, rockets burn fuel very, very quickly. So although they get up to higher speeds and the drag forces increase, they're also escaping the atmosphere where there's less air resistance and they have less fuel. So as the mass decreases, the acceleration actually increases. But here, it's the idea that the acceleration would decrease because we're looking at that initial acceleration. When at cruising speed, the engine power is reduced. Now, this is where being very careful about the question. What I saw was a few people got this next bit sort of a little bit off because they didn't read this part of the question carefully enough. So when at cruising speed, the engine power is reduced so that each engine produces 6 times 10 to the power 4 newtons of thrust, as opposed to the 9 times 10 to the power 4 that you have at full thrust. Okay, which is what happens. Aircraft, they take off and accelerate using maximum thrust or close to maximum thrust, and then once they get up to speed they throttle back the engine to sort of maintain a constant cruising speed. Think planes and cars and trains and stuff, they don't pert along at full speed all the time. So it says, explain in terms of forces why the force is needed to keep the plane flying at constant speed. Well, this is a very standard question. You've seen something very similar to this before. It's the idea that the force needs to balance drag forces or air resistance. Now here, careful, we've got a 2-mark question here, so we want a little bit more than that. So what we want is so that the net force on the plane equals 0, which implies the acceleration is equal to 0. So you need to put that little bit extra to get the 2nd mark here, because if you just mention the idea that it was overcoming drag forces, you've got 1 mark, but really you wanted the idea that it balances, that the net force is 0. So you want to be really quite careful about it. Right. Now, sometimes you're asked to prove this one dimensionally, i.e. with units, but this time it says show that the power of the engine skis may be calculated using this formula below. So you need to actually get into this routine. We know that work is equal to force times distance, and that power is the work done over time. So power is equal to force times distance over time. Distance over time equals speed. So power is force times speed. So what we're looking for here is the idea that you're using the formula for work, you're dividing it by time to get the power, and then realizing that distance over time is going to be your speed. It then says, hence show the power output from both engines combined is 60 milliwatts when cruising. So it's when the force is less, so you've got to be careful. So here the power is the, we're going to assume the force from the engine is 2 times 6 times 10 to the power of 4. That's the force. Don't forget there are 2 engines. If you forgot there were 2 engines earlier on in the question and did the same thing, made the same mistake here, you've got the ECF mark, the aero carries forward, as long as I could see you're working. Multiplied by the speed, cruising speed is 500 meters per second, which gives you exactly 6 times 10 to the power of 7 watts. Okay. It then says calculate the amount of work which would need to be done against air resistance for the plane to travel from London to New York if the aircraft were to travel at cruising speed. So that's going to be actually work is force times distance. Okay. So if the work is force times distance, the force is 5. The force is still 2 times 6 times 10. Oops, I do apologize. Very scruffy. Times 10 to the power of 4 multiplied by distance. Now here we've got to be careful. 15,000 kilometers. That's 15,000 times 1,000. So it's 15 million meters, or 1.5 times 10 to the power of 7 meters. Okay, that's your distance in meters. So if that's the case, then you end up with 1.8 times 10 to the power of 12 joules. Okay, so that's how much work would need to be done. Now the aircraft can carry up to 5,000 kilograms of fuel. Calculate the chemical energy in 5,000 kilograms of fuel. So if we go back to our data table, this again is a skill that engineer has, is that they can find data from tables. So its energy per kilogram is 1.4 times 10 to the power of 8. So 1 kilogram has 1.4 times 10 to the power of 8 joules. That's for 1 kilogram. Well, logically, if we've got 5,000 kilograms, it's going to be 5,000 times the energy of 1 kilogram. So that would be 7.0 times 10 to the power of 11 joules. Now the check here is to actually look at the context of the question. This is about a fighter jet. If we look at the energy required to fly from London to New York, it's far greater. Well, if fighter jets aren't designed really to travel great big long distances, they're meant to be very light, so they have so they never have enough fuel to actually sort of do the journey in one go. And there, if we look at the value here, that would actually make sense. So it's a sense of how do we know that's a sensible value? Well, it makes sense from the context of the question. Now, the next one says the maximum range of the plane at cruising speed. We have to assume that all the energy from fuel is used to overcome air resistance. So here if we're using work is force times distance, then the distance is going to be the work divided by the force. So we assume it's 100% efficient. It isn't, but we're going to pretend. Okay, that's the work done. Divided by that resistance force. Well, if it's still going at cruising speed, it'll still be 6 times 10 to the power of 4 newtons multiplied by 2, because there are 2 engines, which comes out to be 5.83 times 10 to the power of 6 meters. Well, that's about 600 kilometers, which is a little bit, quite a large range for a fighter jet, but it's reasonable value. Next one, describe and explain how the range of the aircraft would be affected if the engine power was increased to make the plane, she should say plane, there's not plane fly faster. Well, if we think about it, if work done is force times distance, so distance is work over force. If it flies faster, that would imply that you have to use more force because there'd be more air resistance to more drag forces to overcome. So it implies more force. So more force, and it'd be the same energy, same amount of work being done. So it would have to be a lower distance. Okay, so it will fly at the same. It will fly with the same amount of energy in its fuel tanks. But if you have more force, then for the same amount of work, you'll have a shorter distance. So that's the question 2. So question 2 always starts off with your SUVAT and a little bit of Newton's laws, and then sort of descends into its sort of energy calculations. Now, question 3 is usually a momentum question. Sometimes I mix 3 and 4 up so that 3 is the graph question, but this is a momentum question. This is actually taken from an old A-level question. So it's all about a wooden mallet being used to hit a hammer to hit a tent peg into the ground. The head of the mallet is a cylinder of a particular dimension, and the density of given the density of wood, you have to show the mass of the head is approximately 1.2 kilograms. Okay, I'm going to be honest. Density is not really in the specification, but there is an expectation that you should have some basic physics and science knowledge prior to actually taking on sort of the University Foundation Programme physics course. So we know the density is mass over volume. So the mass is going to be the density times the volume. Okay, I'm going to put a capital V there so I'm not mistaking it for speed. Want to work out the volume, you've got a cylinder. So a cylinder has got an area and a length. So the length is 0.196 multiplied by the area of the head. So it's half the diameter. So the radius is 0.05. So if the radius is 0.05, we know that's going to be pi r squared, pi times 0.05 squared. Okay. So we know the mass is going to be, we substitute, mass is going to be density, which is 750 multiplied by pi multiplied by 0.196 multiplied by r squared, 0.05. And then we end up with 1.15 kilograms. That's your final answer, which is approximately equal to 1.2 kilograms. Okay, so it's 3 marks. One for recognizing that it's a cylinder, and therefore you had to multiply. You had to work out the area of a circle and multiply it by its length. 1 mark for correct substitution. 1 mark for arriving at something close to the correct answer. The head strikes the tent peg as shown at a speed of 4.2 meters per second, and it rebounds at 0.58 meters per second. Now, careful. Calculate the magnitude of its momentum change in the collision. So we want to work out the change in momentum, which is the momentum before. So the mass is going to be, well, you can either use 1.2 or 1.15, multiplied by its velocity before, which is 4.2. And then you subtract its momentum afterwards. Now, careful, it says it rebounds. So that is going to be minus 0.58. So we're going to subtract, so it's mass is 1.15 multiplied by minus 0.58. Okay, so that's the momentum before, the momentum afterwards is going to be negative. When you subtract a negative number, you're adding in fact. So that comes out to be 5.5 Newton seconds. Because it's a change in momentum, you can say it's Newton seconds. You can use kilograms meters per second as well if you wish, it doesn't matter. The head is in contact with the peg for 0.012 seconds. You have to calculate the average force. Now, if we have the average force, the force is the rate of change of momentum. So it's your previous answer divided by the time, which comes out to be about 480 newtons or so. Okay, so that's the answer there. Again, what I was looking for really was this calculation here. Right. Give a reason why your value for the force will be only approximate. Well, it's because the acceleration is not going to be constant. We're assuming here that the hammer has a constant rate of deceleration. So the acceleration, therefore, the rate of change of momentum is not constant. So the momentum will not change at a constant rate. Okay, that's the idea there. You're actually looking at the fact that it won't change. So that it won't change at a constant rate. So you're kind of assuming that it's that the rate of change of momentum is constant, therefore it's constant force, but actually it's not likely to be like that. So then it says, with reference to your calculations above, discuss whether a mallet with a rubber head of the same mass would be more or less effective in hammering in tent pegs. Well, the collision time would be greater because it's rubber, so it's soft. Okay, so because the collision time is greater, for the same change in momentum, you can abbreviate if you wish. Okay, so the force would be less or reduced. Okay, so that's what we really wanted. Okay, and therefore it would be less effective. Okay, so on to the next question. The next question is your graph question, and it's also your projectiles question. Okay, so it says in this question you need to ignore the effect of air resistance, certainly at the early bits of it. Now, quite a few people didn't attempt the graph question, which is a little bit of a shame. I go to quite a lot of trouble to make these. It says a cannon is used to fire a cannon horizontally at a speed of 30 meters per second. The distance the ball travels varied with the height of the cannon. The ball is fired at a variety of heights and the range of the cannon X is measured. So it's a constant speed of 30 meters per second, and you've got to work out, you've got to sort of look at the fact that different heights here, with it being fired horizontally, would give you different ranges. So the first thing to do, it says, is they made an error in the heading of the table. Correct that error. So what's missing? Well, we've got a missing unit in here. Now, how on earth are we going to work out what the units are? Well, if you look at those numbers and you look at the diagram, it's going to be meters. Okay, you can also look at the diagram from the context of the person stood there. You know you're going to have several meters. So these heights are definitely in meters. The next part is to calculate the 5 missing values of x squared, giving the numbers to suitable numbers in significant figures. And this is only worth 1 mark. So significant figures are essential here. So if you were to square them, you would end up with values. But here we've got 3 significant figures. So the final value should also be to 3 significant figures. Oops. Okay, those were the correct values. You have to correctly calculate them and have them all to 3 significant figures. Okay, these are all 3 significant figures because these values you use to calculate it from are also to 3 significant figures. So it is important to make sure we get that right. The next part is the graph. It says use the graph paper below to draw a graph of range squared, x squared on the y-axis versus the height h on the x-axis and draw a straight line of best fit. So here we've got x squared in meters squared. We've got h, which is in meters. Okay. If you got the unit wrong on the table and you use that unit here, you would not penalize this for a second time on that. Okay. The error carries forward. You are then looking at a scale. So if we look at the scale carefully, well, for the height, so for the range squared, it's going to be near as makes no difference 2000 meters squared. And it goes down to about 182. Well, that's about 10% of the original value. So you can get away with putting the origin on this time. And the same goes with the height. We go up to 10 meters down to 1. So again, you know, that's 10% of that value. So you can put the origin on. So if we look at the range first, we're going to try and go up to about 2000. Now, it's very difficult to do this. The way that I solved this is I used every 4 big squares was 1,000. So every 4 little squares was 100. Now, it's not an easy scale to use. So what I did was I decided that I was going to use, I was going to actually mark every 100 on there. Ordinarily, I wouldn't mark them quite so close together, but actually to make it less confusing, I put my numbers on every 100 so that I could plot correctly. Again, for the height, that was more straightforward. I worked out that every square could be 2 meters, and it would fit on quite nicely because our first value is at 1 and our last value is at 10. So that's only wasting this little bit of the graph paper here. So that was the range. So it's 1 mark for the unit, 1 mark for the range for getting the scale right. And then it was plotting. Now, what I would do as an examiner, just to show you what an examiner would do, I would pick 2 values. I'm going to pick that one, and I'm going to pick that one at random. So at 6 meters, I'm expected to be 1,100. So here's 6 meters. There's 1,000, and every 4 is going to be 100. 1, 2, 3, 4. That's correct. And at a lower value, at 2 meters, it's 369. So at 2 meters, I'm going to go up to 300 here. So that's 350, and that's 375. So it's going to be somewhere in between the two. And as long as that cross is somewhere in between the two, you actually get the plot mark, because you've just got to be within 1 square, 1 small square on your plots. So that's plotted correctly. And well, all of my values fell pretty much on a straight line of best fit. So I drew that correctly. So that's how you get the 4 marks on that. I didn't want to take you through the process of drawing the graph. You guys have seen it several times. If not, go back on my YouTube channel and have a look at the solutions where I have drawn the graph from scratch. Excuse me. You then have to calculate the gradient of the graph, giving appropriate units. And again, when you calculate the gradient of the graph, you go back to your graph and you pick 2 convenient points, one right at the top, one towards the bottom. So if I go for the one at the top here, my point is here, so it happens to sort of land here. And what I'm looking for is, did you correctly give a value of y1? Well, I said it's 1,750. Well, it's exactly halfway between 1,700 and 1,800, so that would be 1,750, so that's correct. And then y2, I said was 300. Well, it lines up perfectly with 300, so I chose my point here. For x1, well, it's 1.6 because there's 1 there, 2, 4, 6. So that's 6. And I said, well, this was 9.6, so this is 9, 2, 4, 6. So that's correct. So what I'm looking for there is a big triangle. And again, when I'm marking, I like to see the big triangle. If I see a big triangle on here, you get 1 mark already for your gradient measurement, even if you don't do anything else. You should then show your working, and the working is pretty similar every time. Remember, your gradient is saying your gradient is delta y over delta x, which is y1 minus y2. You can say y2 minus y1 if you want. It doesn't make any difference as long as you're consistent. So y1 was 1,750. y2 was 300. X1 was 9.6. X2 was 1.6. So if I work this one out first, that's 1,450 divided by 9.6 minus 1.6 is 8.0. So all I then do is you do your calculation. Okay. That gives me 181.25. Well, all my values have been to 3 significant figures, so I'm going to give this value to 3 significant figures, which is 181. The last part of the question, that's worth 2 marks. Last part of the question, giving appropriate units. So if I look back at my graph, units of my y-axis divided by units of my x-axis, so I've got meters squared divided by meters. Just equals meters. So my correct unit is meters, 181 meters for the 3rd mark. D, it is suggested the formula below gives the relationship between the range and the height. So what I've got to do here is I've got to show that it's homogeneous. That should be a squared, by the way. I think it was squared on your one. So the equation is homogeneous. We're going to prove it simply by looking at the units. So we've got x is a distance. So x squared is meters squared. So we've got 4 has no units. V squared, well, that's meters per second squared, multiplied by h, which is meters, divided by g, which is meters per second squared, because it's an acceleration due to gravity. So then we need to just expand that. So that's meters squared, seconds to the minus 2, because we're squaring everything in the brackets, multiplied by meters, divided by meters, seconds to the minus 2. So the seconds to the minus 2, they cancel straight away. And just to show that m cancels with m, I show that. So it's meters squared equals meters squared. Okay, so it is homogeneous. Homogeneous means that on both sides of the equal sign, the base units are the same. It then says, suggest whether or not your graph supports or undermines the theoretical equation. Well, if we've got the theoretical equation here, remember we put x squared on the y-axis and h on the x-axis. So that would be a gradient there, m. So we want to put a little proviso in here. If v and g are constant, then 4v squared over g would be a constant, which would imply the fact the graph should be, well, if it's y equals mx, you know from your maths lessons, that's a straight line through the origin. To imply it's a straight line through the origin. Okay, then you compare your graph. You look at your graph. Is it a straight line through the origin? It's a straight line and it goes pretty close to the origin. It doesn't have to go exactly through it. It's pretty close to it. So it supports it. Oops, that's supported. Okay. So that's the idea. It was the identification that you should have a straight line through the origin if the formula is correct, and the fact that that's indeed what you get, so it supports it. Last but not least, you have to use your value for the gradient of the graph to calculate the acceleration. So the gradient from our graph was 4v squared over g. So g,
Could you please move it down a bit?
Sorry, g is going to be 4v squared over the gradient. So then we substitute 4 times v squared. What was v? Well, if we look back at the question, is there a mention of v anywhere? Go back to the beginning, maybe. 30 meters per second. There it is, right at the beginning. So that's 30 meters per second. So that's going to be 30 squared over the gradient, which I made to be 181, I believe. Did I just double check it? Yeah, 181 meters. So 4 times 30 squared, 4 times 30 squared divided by 181 meters gives me 19.9 meters per second squared, or 20 meters per second squared. We know it should be 9.81, but there we go. The value for acceleration due to gravity seemed to be a lot higher. Maybe this wasn't being done on Earth. It doesn't say it was done on Earth. Okay. Normally in the real exam, you should get, if you ask to calculate G, it should be G on Earth really, but you just go with the value that you've got. It's the technique that's important here. Right. Another question. This is question 5. Well, you know that question 5 and 6 are usually the coplanar forces and moments questions. So you know there's a coplanar forces question here. It says you've got a trolley and an inclined plane or a slope. And if you've got the inclined plane at 1.8 degrees, you have to show the force on the trolley in the direction of the slope is approximately 0.06 newtons. So if the trolley has a mass of 2 kilograms, show the force on the trolley is approximately 0.06. So you're using force, oops, go back to blue pen. Force is going to be the weight of the trolley multiplied by the sine of its angle of incline, okay? That would make sense because the weight, because if you're trying to work out that force there, you know that it's a resultant from the weight and the reaction force. So you know you've got your triangle there, your reaction force, your weight, and your resultant force there, okay? And you know that that would be 1.8 degrees. You know the mg, you're given that because you're given the mass, and you know g because it's on the formula sheet.
Please, can I see the diagram?
Yeah, sure.
Can you explain how the angle there is 1.8?
How the angle here is 1.8 because it's 1.8 here. and this R here is at 90 degrees to the slope. So if that's tilted clockwise by 1.8, then that will have tilted clockwise by 1.8, which means that that angle there is 1.8 because they're opposite angles. They're the same magnitude. Does that make sense?
Yes.
Okay. So mass is 0.2, G is 9.81, and we multiply it by the sine of 1.8 degrees. So if they've got the angle of 1.8 degrees, we can then just work it out where we're expecting a very small number. It comes out to be 0.062 newtons, which is approximately 0.06 newtons. Okay. So again, I've gone to the extra significant figure here to show that I've done my calculation correctly. Now to calculate the acceleration of the trolley, well, it's pretty trivial. Acceleration is force over mass, so it's 0.06 divided by a mass of 0.2, which comes out to be 0.062. I do apologize. You can use 0.6 or 0.062. So that's going to be 0.062 divided by 0.2, which gives you 0.31 meters per second squared. It would be 3. If you use 0.06 here, that would just be 0.30. Okay, so that would be the acceleration of the trolley if we were ignoring air resistance and friction or anything else. It then says the angle of the slope is increased to 3.6 degrees. Describe and explain the effect this will have on the acceleration of the trolley. Well, if it's, I mean, the obvious one is it will be increased. That I would hope was obvious. If you've got a steeper slope, the cart will accelerate more. So if the acceleration will then increase, then that means but we've got to try and explain it. And we don't just want to say, well, because it's obvious, because that's not really explaining it. That's just proof by intimidation. What we want to say is we want to think about the physics behind it. Well, what's the physics behind it? Well, if you've got an increased gradient for the same mg, if that angle is bigger, then that force is going to, that arrow there is going to have to be bigger for everything else being similar. So what we're actually working out here is the fact that the component of the weight in the direction of the slope will increase. Okay, that's your explanation. It's the idea that the component of the weight and the direction of the slope will increase. Now, this question is a real nightmare. I'll tell you why. It's 1 mark. And it says the pupil concludes the acceleration of the trolley is proportional to the angle of slope. Suggest giving a reason whether or not this conclusion is correct. Now, there are 2 possible answers. Because in terms of the actual physics, no, it's not correct. But you don't get a mark for the answer for that bit. It's the explanation. Well, if you think about it, it's not correct because that force is proportional to the sine of the angle, which is not linear. Okay, because the force is proportional to the sine of the angle, then it's not a linear relationship. Okay, however, you can actually say yes. It does, you know, the conclusion is correct because it's the conclusion to their experiment. So could they conclude from the value that the data they've got that that the force is proportional to the angle? Well, actually, those of you who are doing the right levels, you know, doing sort of the higher levels of maths, will know about small angle approximations. But actually, that force and therefore acceleration for an angle of 3.6, which is double 1.8, is actually 0.12 newtons. Okay. Okay. So you got 2 times the angle and 2 times the force, which implies acceleration. So actually, there's no right or wrong answer here. Correctly speaking, in terms of the actual theoretical physics, no, it's not a correct conclusion. But could it be correct from their results? I suppose it could. So you could either answer would actually be fine. And that's quite confusing, I must admit. So if we move on, we then get our moments question. And this is a cantilever bridge. So figure 5 shows a bridge made of a horizontal beam and 2 supports. There is a truck on the bridge. Now you've got to be careful here. State the principle of moments. 1 mark, they just want the simple one. Total clockwise moment is equal to the total anti-clockwise moment for equilibrium. Okay, you can mention about it being about a pivot and things like that if it was worth 2 marks, but here it's only worth 1 mark. So then you have to draw a center of mass symbol where the center of mass of the horizontal beam is. So you've got a horizontal beam here with a truck on it. So you want to put it roughly halfway between, well, it's 13. So I'm going to put my marker at 7.5, I think. Oh no, that's 7 there. So that's 7.5. Does it look about half? That doesn't look like halfway to me. So that'll be, no, it'll be 6.5. I'm being dim, that's why. 6.5. I'm being very dim. It must be morning. Must have only had 1 cup of coffee this morning. So there's my center of mass. Again, I've measured it. You don't have to measure it. It's only worth 1 mark. I just want you to recognize it's halfway along. Then it says the mass of the horizontal beam is 10,000 newtons. So I'm going to put that on before I'm even asked before I even know what the question is. Because I think I can predict the question. It says, by taking moments about the right-hand support, calculate the upward force provided by the left-hand support. So taking the moments about this right-hand support here, okay? So what we do is we think about the moments happening on this side. Well, there is going to be an upward force from the left-hand support, which I'm going to call FL. And we want to work out the distances. Well, if we add all these up, 3 plus 6 is 9, plus 18 is 27, plus 3 is 30. So we know that the center of mass is going to be from here to here. That's going to be 15 meters. So if we want to work out distance from the pivot to the center of mass, then that's 15. That's 3, so that's going to be 12 meters. So we also want to work out the distance between the two supports. That's 18 plus 6 is 24 meters. Okay. And the truck, well, it tells us already is 18 meters away from that pivot. So it says the mass, we want to calculate the upward force provided. So we start off by assuming it's all in equilibrium. So we say the clockwise moment equals the anti-clockwise moment. So in terms of clockwise moment, everything trying to turn, if you imagine the pivot's there, you're looking for everything trying to turn the lever clockwise, which is just that force there, FL. So that's going to be the force from the moment from that force. And we know that FL is 6 plus 18 is 24 meters away. So that's going to be force times distance, 24 FL. The anti-clockwise moment is, well, we're going to look at this, the two forces here. So everything trying to turn it all this way is going to be the anti-clockwise moment because it's the opposite direction to the hands on a clock. So there's going to be the moment from the way to the bridge, which is 10,000 multiplied by this distance of 12. Plus the moment from the lorry, which is 8,000 newtons multiplied by the distance of 18 meters. Okay, so the force on the left-hand side is going to be all that lot, 12 times 10,000 plus 18 times 8,000 divided by 24. And you plug that into your calculator and you end up with 11,000 newtons, or at least I did. Okay. So if you've got 11,000 newtons from the left-hand support, you then hence or otherwise calculate the upward force provided by the right-hand support. Well, if we think about it on here, for every force upwards, there must be equal and opposite force downwards for it to be in equilibrium. So the force upwards here is on the left-hand side, and there's going to be a force upwards on the right-hand side. So if that's the case, then we've basically all the forces upwards must equal the sum of the forces downwards. So the forces upwards, FL plus FR, is equal to the sum of the forces upwards. Well, they've got the truck plus the actual beam itself. And we know that FL is going to be 11,000. So FR is going to be the weight of the truck plus the weight of the beam minus the force on the left-hand side, which is 11,000, which comes out to be 7,000 newtons. And there's your answer. Okay, that's how you do it. The other way to do it is to do exactly the same as you did before, but this time take all the moments about this left-hand pivot. So this would be a clockwise moment of 8,000 times 6 plus the clockwise moment of 10,000 times 15. It would come out. You could work it out and you'd get exactly the same answer. But I think this way is easier. And I don't want to give you extra sort of hard work to do when there's an easy way to do it. Right. The last part of the paper, I've decided to set you some slightly trickier multiple choice questions. Okay. The ones I've been giving you before have been very, very straightforward, and most of you have been able to do them with relative ease. So what we've got here on the last part, the multiple choice questions or multiple guess, are to do with, these are actually past A-level multiple choice questions. So they are slightly trickier. The force resting on the motion of a car is proportional to the square of the car's speed. So the force resisting the motion is proportional to the square of the car's speed. The magnitude of the force at the speed of 20 meters per second is 800 newtons. So what's the useful output power required from the car's engine to maintain a steady speed of 40 meters per second? Well, you know that power is force times velocity. Now the force is going to be proportional to the square of the car's speed. So we know that at 20 meters per second, it's 800 newtons. So if we double that to 40 meters per second, we're going to have 2 squared times 800. So that would give me 3,200. Okay. Multiplied by the speed of 40. So we literally calculate it. And it gives me 128,000 watts. So in other words, 128 kilowatts. So the next one is a rocket flies upwards. So if a rocket's flying upwards, got to think about energy, got to think about this very carefully. As it accelerates upwards after leaving a launch pad, which forms of energy are changing? Well, what have we got here? Well, how do rockets work? They burn fuel. So for burning fuel, if you think back to sort of high school physics, you know, it started off with chemical energy. Okay, so the chemical energy is being used up. What's the rocket doing? It's going upwards. So there's going to be some gravitational potential energy that's going to change, it's going to increase, and it's going to accelerate. It's going to be going faster. So there'll be an increased kinetic energy. So the 3 forms of energy that are changing are chemical, gravitational potential energy, and kinetic energy. Easy mark if you think about it carefully. Now we've got 2 tugs on a rig being shown. Okay. Want to work out the total force on the rig due to the cables in the direction to the east. So we're looking at the force from this tug and the force from this tug. So these 2 tugs are going to be providing a force towards the east. We're ignoring the forces going from sort of going sort of north and going sort of north and south. Okay, we're just looking at forces in this direction. So the component of the force on this tug, well, if we've got the adjacent, we know that it's cosine, so it's going to be 4 kilonewtons times the cosine of 20, which comes out to be 3.76. And here we've got a force of 5 kilonewtons. As all the answers are in kilonewtons, I'm not going to convert to newtons. Multiplied by the cosine of 50. Well, I work that out, that comes out to be 3.22 kilonewtons. I add the 2 together. I get 6.98 kilonewtons. So which one's closest? It's that one. Okay, because if I round it off to 2 significant figures, that's the same thing as 7.0. Okay. Right, number 10. The approximate kinetic energy of an Olympic athlete during a 100-meter race. We've got to use some estimations here. So, well, you know kinetic energy is a half mv squared. Okay, you know it's going to crop up at some point in the exam. So that's a half. Mass of an athlete, well, round about 80 kilograms, I'd say. And running a maximum speed 100-meter race, well, I'm going to say about 10 meters per second. That's roughly what it is actually, but square it. So a half times 80 is 40, 100 squared is 100, so it's 40 times 100, which is 4,000 joules. It's about right. Okay, that's about right. That would be rather high, and that would be ridiculously high. Okay, so that would be the how you do that. You're using estimation, so you're using sort of approximate values, and the way to do it, it's not easy. But the way to do it is to know that the mass of a person is somewhere between sort of, well, it's between 50 and 100 really. So somewhere in the middle of there, 80, 75, something like that. And you know that a sprinter will run 100 meters in about 10 seconds. In real life, they'll get up to maximum speed pretty quickly. So it's going to be about 10 meters per second, very roughly. Even if you use slightly off values, so if I use say 70 here and I use 15 here, it still comes out 4,000 joules as the closest one. If I use my exact estimates, yes, I get it exactly right. But what you're doing is you're estimating and then you're looking for which one is actually closest to the right answer. Right, a micrometer screw gauge is used to calculate the diameter of, is used to measure the diameter of a small uniform steel sphere. The micrometer reading is 5 millimeters plus or minus 0.01 millimeters. What's the percentage uncertainty in the calculation of the volume of the sphere? Now this is hard, so we've got to think about it. So let's put our maths hats on for a brief moment. We know that the volume is 4/3 pi r cubed. Okay. So if it's 4/3 pi r cubed, we know that the radius is the diameter over 2. So if we think about it, it's actually the same percentage error. So the percentage error on the diameter is going to be 0.01 over 5, which is 0.002 or 0.2%. Okay. So that's the that's what it is. That's the percentage error there, 0.2%. But then if it's 0.2%, here we've got r cubed. 4/3 is a number, pi is just a number, so that's not got uncertainty. So the uncertainty in the volume is going to be 3 times the percentage uncertainty of the radius. So it's 0.2 times 3 because it's r cubed. So that would be 0.6%. Okay, you have to think about that one. Number 12.
Gary?
Yep.
Gary?
Yep.
Could you please go to the last question? I have a question.
Yeah, sure.
Can you the way you calculated the percentage uncertainty for the radius, could you also do 5.1? Could you do range divided by 2? Like 5.1 minus 4.9.
5.1 minus 0.02. What that would actually give you is the actual uncertainty, not the percentage uncertainty.
I mean, if you do 5.1 minus 5.01 minus 4.99.
Yeah, you could do. Well, let's do that as an exercise. We've got a bit of time, so I think it'd be a good idea to actually do that as an exercise, just to see if that does indeed work. I've always said that if you use correct methods, you get the marks. So let's prove that it works. So we know we're using maximum minimum values. We know the volume is 4/3 pi r cubed. So the maximum value here is going to be 4/3 times pi. Well, if we keep it all in millimeters, so we end up with millimeters cubed here, it'll come out. So 4/3 pi times 5.01 cubed. So 4/3 times pi times we've got a key button, yes I have, cubed, 5.01 cubed, comes out to be 527. Okay. Seems quite high that, but never mind. The minimum value is going to be 4/3 pi times 4.99 cubed. So that then comes out to be 520 millimeters cubed. So the uncertainty in the volume is going to be 527 minus 520, okay, over 2, which is going to be 7 over 2, which would be 3.5, okay. So if we work out the uncertainty in the volume divided by the volume to get the percentage uncertainty, it's going to be 3.5 divided by the median value, which should be, which is 524. Which comes out to be 0.0067 roughly. Okay, so in other words, 0.67%. And then if I work it out here, if you look at the actual options, well, the one that's closest is C. Okay, so it does come out, it does work. So it is valid to use, but just bear in mind, because we're doing it in steps and rounding off, it's going to be slightly off. But you can see that you can work it out that way. Sorry,
Gary, you know how to find the absolute uncertainty. We do range over 2.
Yep.
Could we use 5.01 and 4.99 as the range for the micrometer reading?
No, because you're looking at the uncertainty in the volume, not the uncertainty in the diameter.
No, I mean like when we're trying to calculate the uncertainty in the radius, like you did earlier.
Well, you're given the uncertainty in the radius. I mean, if you did it that way, if you said, well, the maximum radius is going to be, and I've realized I made a bit of an algebraic error here, but it actually comes out in the wash. It actually does come out in the wash. If you want, you're saying that you want to work out your maximum value for radius. Well, maximum value is going to be 5.01 over 2, which is 2.505. The minimum value is going to be 4.99 over 2, which is going to be, I've got to get this right. It's going to be 2.495. So the range is going to be 2.505 minus 2.495 over 2, which is 0.005 millimeters, sorry. Okay, which is exactly the same percentage error, because if I want to work out the percentage error, then that's going to be 0.005 over the radius, which would be 2.5. Which is 0.02. Okay, so it's actually still 2%, as it was when I calculated it from the diameter. But actually, because it's just the R, the radius is the diameter divided by a number with no uncertainty to it, then the percentage errors are going to be the same. So you could do it the easy way. Okay. Moving on, question 12. The graph shows a variation of velocity with time for an object. Now, we've got to be careful here. You want to work out the displacement and the acceleration. So the acceleration is the gradient. So it's the change in speed, so the acceleration is going to be the change in speed over time. So it's change in velocity, so it's going to be 24 minus 4, which is 20, over a time of 5 seconds. That will be 4 meters per second squared. Okay, so all the ones where the acceleration is 4 meters per second squared is correct. Those two are not, so it's not C and not D. You want to work out the displacement, you're working out this area here. So this area is a trapezium. So the displacement is the area of a trapezium. So it's small width plus large width. So that's going to be 4 plus 24 over 2 multiplied by height, which is 5. It's a trapezium. Okay, which comes out to be 70, because, okay, just double check it. 4 plus 24 equals, divided by 2, gives you 4 multiplied by 5. Double check it. I got that right. No, hang on. 4 plus 24. So that's 28. Divided by 2 is 14. Multiplied by 5, 70. There we are, 70. That makes sense. Okay. I could tell straight away that what I'd originally calculated, I'd typed it incorrectly into the calculator because it actually wasn't in among the options here. So this one has a displacement of 70 meters. So it's got to be B because they're both correct. Okay. Right. Next question. Number 13. It's a concept and its vectors. The nucleus collides with a stationary nucleus in a vacuum. The diagrams show the paths of the nuclei before and after the collision. Which diagram is not possible? Well, if we think about it, if this nucleus is traveling horizontally, then any momentum, so any component of momentum this way, because it's a vector, there must be a component of momentum with the other particle going that way, going downwards. Otherwise, we're not conserving linear momentum. So here, we could be conserving linear momentum. Here we could, because this one could be traveling a lot faster. So that's got, this one's got momentum downwards. There's a component downwards. Here's a component upwards. The only one where it doesn't work is this one, because when they actually collide, and move off, then here this one has a vertical component of momentum, and this one has a vertical component of momentum. And when you add the two together, they're not going to cancel out. There's no way they could. So if that's the case, then C is the one that's not possible. Right, last but not least, number 14. Which of the following is a statement of the principle of conservation of momentum? So we've got to remember what momentum says. Well, we're saying,
Sorry.
Yep.
Can you explain me again exercise 13?
13, yeah, sure.
Yes.
Right. If we think about it, what we have to think about is we have to look a little bit beyond just the basic knowledge. We know with any collision, with no external forces, we know that momentum is conserved. But we have to remember that momentum is a vector. So because momentum is a vector, we have to think about the momentum in different directions.
Yeah.
So we have to think about the momentum in different directions. So here, obviously, the horizontal momentum can always be conserved. But what's obvious here is if we think about the momentum always in this direction, if we think about the momentum at right angles to it, then the two sort of paths, there must be one particle moving down and one particle moving upwards. Otherwise, there would have to be an initial momentum in that sort of upwards or downwards direction from the particle before the collision. And that means that we'd be breaking the law of conservation of momentum, because it doesn't, obviously. Because remember, all vectors at right angles have no effect on each other. So the momentum in the vertical direction must be 0. So the momentum of the particle moving in this direction, the vertical component must be going upwards. That one must be going downwards. Okay. Similarly here, we can see here, we have, if we look at the perpendicular component of momentum, one of these has a component going upwards and the other one has a component going downwards, so that the vertical momentum they cancel each other out. In this example, it doesn't happen because they've both got momentum in the same direction, same vertical component, so they've both got their vertical component of their momentum in the same direction, so they can't cancel out. And that's why it's C. Okay.
Yes.
Right. Thank you. Question number 14. Which of the following is a statement of the principle of conservation of momentum? Well, it says an elastic collision momentum is constant. Well, it's not. It's true, but it's not really the principle of conservation of momentum. That's more sort of confusing. Elastic and elastic collisions. It's a little bit. It's not quite right. Momentum is the product of mass and velocity. Well, it is. It's mass times velocity. But that's not the idea about conservation of momentum. The force acting on the body is proportional to the rate of change of momentum. Well, that's the idea about impulse, isn't it? And that's Newton's second law of motion. So what we're left with is the momentum of an isolated system is constant. In other words, the total momentum before equals the total momentum afterwards, provided there are no external forces. So D was the answer there. Okay. So they're pretty tricky multiple choice questions, and that's something I'm going to give you in your next paper. Now, this is obviously the last paper of the half term. What I'm going to advise you to do over the half term, I think, what I'd like you to do is, obviously you've got your practice papers and you've got your walkthroughs, and you can use those to sort of do some revision. But you've also got your student guide for Unit 2. Okay, I emailed those to you at the beginning, or gave them to you at the beginning of the unit. And in there, you've also got, inside that front cover, you've got your sort of your checklist. What I would like you to do is really, over the next week, is just really get your head in that book and make sure you've revised. Okay? And then what we'll do is I'll give you a practice exam in the first week back. Everyone okay with that?
Yes, sir.
Yeah.
Okay. Right. So thank you very much for paying attention. I know it's been an hour and a half of listening to me talk again, but I think this does seem to be yielding sort of better and better results. So I want you to keep going with that. What I think we'll do is I'll sign off there. Do make sure that you're, as I say, that you're doing your sort of your revision over the half-term break. Remember that you've got a lot of a lot to sort of try and remember. You've got about two weeks before when you come back. You've got about 2 weeks before you come back, before you actually hit your real exams, which, if you're on site, are probably going to be in the King's Hall, the way things are going at the moment. Okay. If you're not on site, what will happen, as I say, is it'll be sent to you via Show My Homework. Right. So have a good half term. Do some revision. Any problems, send me an email and I'll answer them as best I can. Right. I'll see you all after the break, after the half term break.